Today we are going to discuss the topic called Kronig-penny model. The Kronig-penny model actually investigates the behavior of electrons in a periodic crystal lattice. The potential experienced by electrons is approximated as a series of square wells and barriers, which is shown in the figure. Here is well and also the barriers. This model allows us to analyze the allowed energy values for conduction electrons within the lattice. By solving the Schrodinger equation for this periodic potential, one can derive the quantized energy levels that characterize the electronic structure of the material. Here we are going to study the behavior of electronic potential. In order to study this electronic potential, we have to consider the square well potential, which is shown in the figure. The square well potential that we considered is one-dimensional potential well. Thus, the potential energy of an electron when it moves in one-dimensional perfect crystal lattice is assumed to be in the form of rectangular wells. Here we have to use Schrodinger equation for solving the problem. According to the Schrodinger wave equation, we can write d square psi by dx square plus 2m by h cut square into e minus v into psi is equal to 0. That is equation number 1. While considering this periodic potential, there are actually two regions, that is the first region and this is the second region. First of all, we should consider this equation for the region 1. Here the region 1 is from 0 to A. Here inside the well V is equal to 0. That means the potential is 0 here. When putting V is equal to 0 in the equation 1 becomes d square psi by dx square plus 2m by h cut square into E psi is equal to 0. This is equation number 2. For simplicity, we can put 2m e by h cut square is equal to alpha square. Then equation 2 becomes d square psi by dx square plus 2m by alpha square. We can put alpha square psi is equal to 0. That is, we put alpha square for 2me by h cut square, then the equation become d square psi by dx square plus alpha square psi is equal to 0. This is our equation number 3. While we considering the second region, the potential is V0, that is the second region is this barrier region. Here the potential is V0. That is, when we considering the region 2, the potential we can write it as V0. Since the potential for the region 1 is V is equal to 0, we substitute and solved for the Schrodinger equation. Now we want to consider the second region where the potential is V0. Here for region 2, we want to consider from x from minus b to 0 and v is equal to V0. Then the Schrodinger equation for the region 2 becomes d square psi by dx square plus 2m divided by h cut square into e minus V0 into psi is equal to 0. This is equation number 4. In the above equation, we can substitute 2m by h cut square into e minus V0 is equal to beta square. Then the above equation, that is equation number 4, becomes d square psi divided by dx square plus 2m by h cut square into e minus v0, that is beta square. Psi is equal to 0. That is, here in this equation we want to write d square psi by dx square plus beta square psi is equal to 0. This is equation number 5. For the region 1 and region 2, the solution is obtained from Bloch's theorem, that we have already discussed about the Bloch's theorem in a session. And here, according to the solution of the Bloch's theorem, we can written as psi is equal to e raised to ikx into uk of x. Here, uk of x is a modulating function which modulates the plane wave e raised to ikx. Then the Bloch's theorem, the solution from the Bloch's theorem, we can written as psi of x is equal to e raised to ikx into uk of x. That is equation number 6. Now differentiate equation 6 and substitute in the equation 3 and 5. We get p sin alpha a divided by alpha a plus cos alpha a is equal to cos ka. That is equation number 7. We know that what is alpha. Alpha. Since alpha square is equal to 2me by h cut square, alpha is given by alpha is equal to root of 2me divided by h cut. That is alpha, and here p is given by m v0 ba divided by h cut square, that is p. Here p is scattering power of potential barrier. P is nothing but what is p? P is scattering power of potential barrier. It is important, very important to remember the value of P, that is the scattering power of potential barrier. While we considering a crystal lattice, P is the strength with which electrons in a crystal are attracted to the ions. And this P is the measure of this strength. In the equation, there is two parts, left hand side and a right hand side part. In the LHS part, the equation is P sin alpha a by alpha a plus cos alpha a, and in the RHS there is cos ka. We know that for the cos function, while we considering the right hand side, the cos function, the maximum limit, the value of cos function lying between plus 1 and minus 1. For the detailed analysis, we have to draw a graph between P sin alpha a by alpha a plus cos alpha a versus alpha a. Here is the graph representing P sin alpha a by alpha a plus cos alpha a versus alpha a, where alpha indicates energy. We know that alpha square is equal to 2me by h square square. Hence alpha is also talking about energy. And y-axis here is P sin alpha a by alpha a plus cos alpha a, which is actually equal to cos ka. Then the maximum of cos function, maximum and minimum values lies between plus 1 and minus 1. That is shown in this graph. That is plotted in the graph, that is plus 1 and minus 1. Here is the plus 1 region and here is the minus 1, and it is the origin. While we are drawing the graph, For y-axis p sin alpha a by alpha a, we get this but the values admissible for energy, the allowed energy is only lies between +1 and -1. Hence the values beyond +1 and -1 is not admissible. That is, this is beyond +1 and this is also beyond -1. But this is not allowed and hence this region is not admissible and it is called forbidden band. And the shaded portion, while we considering this portion, we know that it is in between +1 and -1, hence it is allowed band. Here also between -1 and +1, this is also allowed, and the next this is between the next shaded region is also allowed. And in between there is when there is beyond the limit, beyond +1 or it is when beyond -1 the regions are not allowed, hence these bands are called forbidden band. Hence in this graph the shaded regions are allowed band and the unshaded portions or bands are forbidden bands, and the values are admissible when it is lies between +1 and -1. And from the graph we can conclude that energy spectrum of an electron consists of large number of allowed band and also forbidden energy band. And also we can conclude that the width of allowed energy band increases with the increase of energy value. In the x-axis we are talking about energy since we have drawn the graph of alpha A, while in the x-axis we consider alpha A which is talking about energy, and for the x-axis it increases, and as it increases we know that the shaded regions width is also increases. That means the width of allowed energy bands increases with increase of energy value. Now we have to consider the situation in which P turns to 0. When P turns to 0, P means we know that scattering power of potential barrier. When P turns to 0, the term P sin alpha A by alpha A turns to 0. Then we can write cos alpha A is equal to cos Ka. Then from this equation, cos alpha A is equal to cos Ka when alpha A is equal to Ka. Then we can write alpha is equal to K. Then we can write alpha square is equal to K square. Then we can substitute the value of alpha square. We know that alpha square is equal to 2me by h cut square, that is equal to K square. From this equation we know that h cut is equal to h by 2 pi. Substitute this value in this equation, then we can write 2me divided by substitute for h cut, then h by 2 pi. Since it is h cut square, then h by 2 pi the whole square is equal to K square. From the above equation, we can write that this denominator, the lowest denominator can be 8 for 2 square 4 into the numerator. That is, we can written as 8 pi square m into e is equal to K square into h square can be given to the right, then K square h square. Then we can write E is equal to h square K square divided by 8 pi square m. We know that this equation represents the free electron model. This means that inside the well the electron has some potential energy. and the energy is capital E, and it is obtained as h square k square divided by 8 pi square m, and this is called Kronig-penny model.